All right, thanks for coming to my talk. I'm very excited to share with you my recent study of the history of the theory of lift. As you may know, I'm very interested in general in the history of science. I did several lectures before on the history of mechanics, history of the principle of least action, history of fluid mechanics, and history of aerodynamics, and this is the fifth topic on the history of the theory of lift. In my previous study on the history of aerodynamics, I mainly relied on these four references: History of Mechanics by René Dugas, History and Philosophy of Fluid Mechanics by Grigori Toccati, the von Karman's book on aerodynamics, and Ackroyd's book. So in this lecture in particular, I will mainly focus on the narrative by David Bloor in his masterpiece, The Enigma of the Aerofoil. It's the most encyclopedic book on the subject. In fact, we aeronautical engineers are very lucky that David Bloor has decided to write on this subject, which is near and dear to the heart of every aeronautical engineer. It's a 550 pages book that tells a very rich story on the history of the subject from the eyes of a sociologist who relates the evolution of the theory to the underlying incidents in World War I politics and press. I studied this book in detail and I summarized it in a 90 pages document, and these two lectures will provide summary of the summary. So it's far from being complete. I apologize from the beginning that many interesting and important stories will have to be neglected. So let's start. This is the beginning. December 17, 1903, Wright brothers made the record of the first powered flight. But unfortunately, at the time, there was no guiding principles, no mathematical theory that can answer even simple questions in aeronautics, like how much lift a wing can generate, for example. The Wright brothers had to rely, thanks Bill, thanks Dimitri, please. They had to rely on their amazing engineering skill, engineering ingenuity, and tons of wind tunnel tests. So to come up with a successful model and make history. So this is summarized in a nice letter from Lanchester to Colonel Fullerton, the honorary secretary of the Aeronautical Society. So Lanchester wrote that I think it was a mistake of the Aeronautical Society giving the Wrights a medal for their contribution to aeronautical science. I agree with their having the medal, of course, but it should have been for what they have done. So basically he's saying they contributed nothing to aeronautical science. They were very good with engineering ingenuity and hands-on skill to build a successful model, but they did not contribute to the science itself. So fast forward 1909, first cross-channel flight from France to England by Louis Blériot. Newspapers next day coming with titles like "Britain is no longer an island," "The nation's basic line of defense is breached," "The channel is no longer a mode that makes the island impregnable fortress." So you can see from the dates here that around this time there was already political tension in Europe, and the emergence of this new machine may make things more inflamed. So this is why when the Wright brothers visited Europe in 1909, some newspapers in England, they tried to put pressure on the government to buy planes from the Wright brothers to be ready in case war emerges. So you can find the Flight newspaper said, "It may be taken as assured that our government will duly acquire Wright aeroplanes, and the famous American brothers will themselves instruct the first pupils in England." So the Secretary of War at the time, Richard Haldane, had a different opinion. He was a highly intellectual person, combines politics or philosophy, law. He actually translated Schopenhauer. He had a passion for Hegel. Was a highly intellectual person, and he viewed the Wright brothers as empirics. They built their airplanes by trial and error. This is his view. So he wanted a more scientific approach to airplane design. He did not like to buy the Wright airplanes. So he wrote afterwards, "The newspapers and contractors keep clamoring for action first and thought afterwards. whereas the energy which is directed by reflection is the energy which really gives the most rapid and stable results. So he decided not to buy the Wrights airplanes, and he formed a subcommittee of the Committee of Imperial Defense to study these, the dangers coming from this new machine, and how much money should we spend and in what direction. And then he formed another committee of the subcommittee, this time by scientists under Lord Rayleigh. That was the Advisory Committee for Aeronautics, ACA. Several years later, our NASA was established on the same model and actually under the very similar name, just adding the word national at the beginning. So the ACA, Lord Rayleigh was the president, Glazebrook was the chairman, both came from Cambridge. The plan was as follows. Army and Navy will build airplanes, and whenever they encounter technical problems, they will send it to the ACA, and people at the ACA will turn these technical problems into specific scientific questions, send them to the National Physics Laboratory for experiments. To me, this is the way, this is ideal. Obviously, it was not ideal for many others, and for the political opposition and newspapers, they saw it as too theoretical, less practical, too scientific, So some generals, they said, shouldn't scientists be on tap rather than on top? So probably the first question to the audience here, do you support Haldane's decision of not buying the Wrights plane and forming the ACA? Do you say, yes, I like the decision, or no, the war is at the doors, we need quick actions? Anyone who says, yes, I support Haldane's decision? No? Everybody will buy airplanes? Yeah. All right, so now 100 years after we... What? I'm sorry, Bill?
I didn't buy an airplane. I had no consequences all over.
Okay. So 100 years later, now we can look back and assess Haldane's decision. It turns out to be not too bad, actually, because in the years to come, there were many crashes in the US Army of the Wright airplanes. In particular, Model C, all 6 airplanes crashed. And here is a report in the 1920 to the ACA by a test pilot reporting on the flying capability of the Wright airplane. He said, it needs an equilibrist of the first order to maintain a stable flight. So it was a highly unstable airplane that requires continuous attention to keep stability in flight, which will distract the pilot from performing the actual mission. Later on, when the aeronautical community learned the concept of flying qualities, the effectiveness of an airplane to perform its mission, now we can look back and assess the flying qualities of the Wright airplanes, which was already done in a 1985 paper by Jex and Collick, and they concluded that the airplane has very poor flying qualities. So Haldane's decision was not too bad, because the Wright airplanes seems that they wouldn't be very useful to the Royal Air Force anyway. All right, now let's do some digression, because the composition of the ACA, the Advisory Committee for Aeronautics, were mostly from Cambridge folks. So let's do a little bit of digression here to talk about the Cambridge Mathematics Tri-Pass exam. It was a very important exam for people at Cambridge, based on which many fellowships and prizes were decided. So they used to rank students. Top students were called wranglers, like senior wrangler, second wrangler, and so and so. The order was published in the Times magazine. You can see this was something, And the senior wrangler used to receive a celebrity-like treatment. The exam was quite competitive, as you can imagine. And actually, some professors used to include in the exams some of their research problems as exam problems. In fact, in the year 1854, one of the problems was to prove what we know now as Stokes' theorem. So the exam was full of mathematical tricks. Almost never you can attain the status of a wrangler without intensive coaching. In fact, in the book, Masters of Theory, The Rise of Cambridge Mathematical Physics, Warwick, he included an appendix that includes a list of all wranglers, colleges, coaches for 44 years. Here I'm just showing a couple of years. And you can see the name of Ruth, very prominent as a coach, actually. In fact, Ruth was a senior wrangler in 1854 over Maxwell himself. And Ruth has coached many of the people we know: Rayleigh, Lamb, George Darwin, the son of Charles Darwin, Brian of the stability theory, or for the Orr-Sommerfeld equations. And most of the famous people we know, they were wranglers, not necessarily coached by Ruth. For example, here is Clifford of Clifford Algebra, Bertrand Russell, Hardy, you name it. So probably most, if not all, the prominent English scholars of the time, they were wranglers. Right, now going back to the ACA composition, it was composed of 12 members. Out of these 12 members, 7 fellows of the Royal Society. I'm sure that Professor Sorignano will like that. 6 were wranglers. 3 were officers from the Navy and Army. And 2 were what they call at the time practical men, like practical engineers. Lanchester, which is a main character with us today, and O'Gorman, the head of the aircraft factory. The main criticism was it's a committee for wranglers. So the newspapers came criticizing them as it's a committee of professors, not producers, too many theorists. Where are the practical men who are doing the work? Like, where is Handley Page and Rolls and all these names? So Lord Northcliffe actually criticized it as one of the most lamentable things. He called it Haldane's collection of primeval men. So Flight newspaper, they wrote this: the opinions of the practical men who are doing the work are worth more to the nation than those of a miscellaneous collection of scientists. Of course, they were not patient at all until the ACA gets some results. So within a year, they started criticizing the lack of results already. So the Aeronautics Journal, for example, they wrote, the committee is bound largely to be a failure so far as results of immediate practical value are concerned. Just within a year, they judged this. The situation was exacerbated even more after the competition at the Royal Aircraft Factory in 1912. They made a competition for private companies. No government entities were allowed to participate. Every private company will participate with its own airplane. It will have to pass some flight tests. And the company with the winning airplane will be contracted by the government to build some airplanes to the army. That was the deal. People at the Royal Aircraft Factory allowed the BE-2 airplane, which was designed by de Havilland at the Royal Aircraft Factory, to informally participate in the competition. This is a government airplane. They just wanted to pass the same flight tests as the private airplanes. All airplanes failed miserably. The BE-2 did exceptionally well, showing stability, good speed, and de Havilland even made a new altitude record during the competition. Unsurprisingly, the War Office decided to build the BE-2 instead of the official winning airplane. This infuriated private firms and political opposition. And around that time, during the early times of aviation, the accidents rate were high. The BE-2 had its own share. So the political opposition and the associated newspapers, they exploited every accident, every tragedy of the BE-2 to point to the inferior design of the BE-2 and the incompetence of the government entities in general in comparison to the private sector. So, for example, the aeroplane came with a headline, March 19, 1904, The Victims of Science. They literally wrote that it was the scientific approach to airplane design that had killed these unfortunate men. So it reminds me, of the recent movie, Don't Look Up. Fits nicely. So the situation was inflamed even more in the summer of the next year. This is after the war had already started, the Fokker Scourge incident. So Anthony Fokker, he equipped one of the German airplanes with a forward-firing machine gun that is synchronized to fire with a propeller. That was very nice. And the plane itself was a mono-wing, so it was maneuverable than the BE-2 bi-wing, which is more stable but less maneuverable. This gave the German an advantage over the British during that summer, leading to the loss of some airplanes and people. And this was the pretension that the opposition wanted. So Pemberton Belling, he was one of the members of the parliament, founder of the Supermarine Company. He was one of the supporters of the private firms in the parliament. So he described the government entities as murderers inside the parliament. So that was, you can see that due to the seriousness of these allegations, the parliament has to form two committees for investigation, one for the Royal Flying Corps and one for the Royal Aircraft Factory. The first committee did not find violations from the Royal Flying Corps, but the second committee, they concluded that the rights of the private sector have been encroached upon. And they demanded governmental support for aircraft private firms. So under this extreme pressure, the government had to shut down all the design, build and fly activities at the Royal Aircraft Factory, which was a very sad decision because before leaving, O'Gorman and his colleagues at the Royal Aircraft Factory, they designed and built one of the best airplanes of the time, the SE-5. Actually, Lord Douglas, Marshal of the Royal Air Force, he described it as the best fighter in Britain in World War I. This expression, reptile aeronautical press, was the expression by O'Gorman, the head of the aircraft factory. And Bloor concluded that this episode must count as one of the most disreputable in the 20th century British politics. So I'm just giving you background of the underlying political and military tension. Now let's go to our science. With all that, the action of the air on the wing remained an enigma. So you can see that, using the names of George Bryan, the founder of the stability theory, the Germans are probably putting their best brains into improving their aeroplanes. And as Greenhill portrayed it in his 1914 Nature paper, it's a mathematical war. So basically, right before and during World War I, there was a parallel mathematical war between the two nations, Germany and England, to develop two theories, one for stability and one for lift. This lecture is focused more on the lift, not more actually, wholly on the lift. And you can ask, what's going on? I mean, why is it a big deal? This is in the 20th century already, and it's a classical problem in physics. It's not relativity, it's not quantum mechanics. We know the equations of motion, force equal mass times acceleration. What is the issue? Yes, we know the equation of motion, but in order to apply the equations of motion, you need a model. In fact, even Newton himself, he adopted different models for the air. In one of his models, he considered the air particles as, interacting with each other. In another model, as composed of infinite number of particles not interacting with each other. In one of his models, for example, he considered the air composed of infinite number of particles moving in straight lines until they strike an object. And once they do that, they lose their momentum normal to the object, resulting in a normal force. This leads to the famous sine square law. And but well before this time, physicists and fluid mechanicians realized that this is not the right model for air, and a better model would be through what we call the fluid element, which allowed us to use differential calculus in conjunction with the equations of motion to come up with a good model for the fluid continuum. Now the equations of motion are Navier-Stokes equations. Yes, but we need assumptions. We cannot, go and brute force solve Navier-Stokes equations at the time. So we need assumptions. So the best assumptions at the time were, although really air is compressible, but at the time flight was occurring at small speeds, like 70 miles an hour. And in fact, up to 200 miles an hour, the error in incompressibility, the error in density, due to this incompressibility assumption is within 3%, which is very reasonable. Also, air has very small viscosity, and the thought at the time was a theory for zero viscosity fluid will be good enough, should be good enough for a fluid with small viscosity. David Bloor expressively stated it in, if you add the fiction of zero viscosity combined with the fiction of total incompressibility, this makes an ideal fluid. It's a fictitious concept, all right? And if you accept these two assumptions, you get, the Euler's equation for an ideal fluid. And even with this whole set of assumptions, it's not enough. We cannot obtain a theoretical or analytical solution for the Euler equation even today. So we need more assumptions, and hopefully they should be brilliant in the sense that reasonably accurate and also enabling, allow us to do something that we could not do otherwise. That was the aerorotationality assumption, which simply assumes that fluid elements, while moving, they do not rotate around themselves. If you accept this assumption, then Euler's equation reduces to the Laplace equation, which is very happy coincidence. Why? Because this set of equations appear ubiquitously in physics. In gravitation, heat, elasticity, electromagnetism, electricity, you name it. So we have huge legacy to exploit. In fact, Maxwell himself exploited the analogy between hydrodynamics and electricity to solve the flow through an orifice. This is why these potential flows are sometimes called electrical flows. Fine, so now we know how to solve this equation. We have huge legacy from all other branches. Let me give you just one way of solving these equations, which is quite interesting. A function f that satisfies this equation is a differentiable function. Differentiable function in the complex domain, we call it holomorphic. All right? Also, a function f that satisfies this equation, it represents a flow field over some body. So this means that any holomorphic function, any differentiable function, represents the flow over some body. Give me any differentiable function, it immediately represents some flow field, which means that we can construct flow fields with a blink of an eye. You know, give me any differentiable function, it represents some flow field. So let's try together. What is the simplest differentiable function of non-zero derivative? Well, it's f of z equals z. This represents a free stream. Not so exciting. What about another suggestion? Well, what about 1 over z? This represents a doublet, which is the hydrodynamical analog of an electrical dipole. Again, another fictitious thing. What about the addition of the two? Well, it represents the flow over a circle, which is a very realistic thing. So now we're talking, right? Now we're very happy, because now we have the flow field in the entire domain. Velocity at every point, pressure at every point. In particular, over the surface, we can integrate and get the force. And here is another happy coincidence. There is the Riemann mapping theorem, which implies that give me any nice shape in the domain, I can always convert it into a circle. So now I can solve the flow field over any shape. I will convert it into a circle where I already know the flow field. We're done. And if you do that and get the force on the circle, you get a zero force. Not only on the circle, on all shapes, which is quite disappointing. So when we thought that we got it all, we got nothing. So that is the D'Alembert paradox, which is in Germany was called Dirichlet paradox. So we need to relax one of these assumptions, and luckily Helmholtz and Kirchhoff, they realized that actually we can have more solutions. The zero force solution is not the only solution. So for the Laplace equation, we just need to relax the aerotationality assumption in a smart way, and we will get lift and drag and everything. So from the Laplace equation. So the issue is, so here is the point. If you give me a way to relax the aerotationality assumption, this will represent a theory of lift. So at the time, there were two competing theories of lift, one in England and one in Germany. Interestingly, the one in England appeared first in Germany and vice versa. The British theory was the discontinuity theory of lift, which, like I said, appeared first in Germany by Helmholtz and Kirchhoff. So Helmholtz considered this extreme example, a flat plate that is meeting the air at a right angle. It's like you cannot give me zero force for this. Ironically speaking, if you solve the flow field in the classical way, you will get a zero force for this. It's agnostic to the shape and the angle of attack. It doesn't matter. So anyway, so he relaxed the pure aerotationality assumption as follows. He allowed sheets of discontinuity to emanate from the sharp trailing edge, sharp edges, both edges. And he modeled the air behind the plate as a dead air, stagnant. So this already breaks the symmetry between the flow in front of the plate and behind the plate. So it will cause force, for sure. All right? So that's the Helmholtz. Then later on, Rayleigh used the same line of thought, the same theory in England now, to solve the flow over a flat plate at a smaller angle of attack, more representative to flight. All right? But he used the same theory in the sense we have sheets of discontinuity emanating from the sharp edges, dead air on the top of the plate. all right? So this will cause a normal force to the plate, and here is a nice expression for the normal force, all right? From which you can compose to lift and drag. Let's look at the lift coefficient, variation with the angle of attack. Let's look at that. This is interesting. The red curve here is the Newtonian theory, sine square law. Blue is the Rayleigh's theory. Black is the classical theory that we currently teach in everywhere in our aeronautical engineering schools, which is close enough to reality. As you can see, both the Newtonian theory and Rayleigh theory underestimates lift significantly. So nature is much more generous than what Rayleigh and Newton had thought about lift. And in fact, some people even blame Newton for the delay of aviation, because if this formula for Newton were to be correct, aviation wouldn't be possible. So some people blame Newton that because of the very small lift and large drag associated with his model, it might have discouraged some people from pursuing aviation. But anyway, so at the beginning, at the ACA, the Aeronautics Committee, Advisory Committee for Aeronautics, the main business was the discontinuity theory of lift by their president, Rayleigh. Extended theoretically, verified or validated experimentally, tested experimentally, and so and so. So as early as 1909, this is the first year, an experiment by Munk, he compared the theory to experiments, and he found that there is great difference, as we already pointed out. Not only that, he found that the main lift in reality comes from the suction side, on the upper side of the airfoil, not from the pressure side. This is in contrast to what the theory was suggesting. The theory was suggesting something like the air is pushing, you know, the flat plate or the wing like this. This is not how lift works, right? So follow-up report by Stanton found that the center of pressure suggested by the theory is actually behind the actual one. Another follow-up report, they found that a significant effect of the shape of the upper surface in controlling lift, which is completely ignored by the theory. So simply, we're talking about a wrong theory, both qualitatively and quantitatively. And here is the bothering thing. I already showed you in the first slides the amount of political tension and military tension, and at the ACA they were formed, you know, to handle this, and they found that this theory is a wrong theory, even though they did not stop working on it because it was mathematically interesting. So as late as 1914, Bryan and Greenhill were still publishing on the discontinuity theory of lift, which may really seem to confirm the statements by the generals that scientists should be on tap, not on top. So anyway, this obviously widened the gap between practical men and the advisory committee, because if you're not providing something useful, the practical men will find their own way, right? Will do it their own way. So you can see the Aeronautics Journal actually writing, ask Eiffel for the air resistance of, say, an airship hull, and the job is done in a couple of days, while it would last heaven knows how many weeks at the MPL. So this led to the emergence of what Bryan had called new Newtonians. People like Newton model, so it's simple, sine square law, the angle of attack. It underpredicts the resultant aerodynamic force. Well, we're going to add a correction factor S. So they called them new Newtonians. So that was basically an empirical equation, you know, that fits the data. So that was the state of knowledge in England right before the war, as stated by David Bloor. On the eve of the Great War, none of the British workers in the field of aerodynamics had any workable account of how an airplane could get off the ground. And as you can imagine, the war will have its own demands. It will not allow fundamental studies. So the British aerodynamicists did not get off the war better than before it. So you can see here George Thomson, the son of the Nobel laureate J.J. Thomson. He wrote a book on applied aerodynamics as late as 1919. This is after the war. He is writing, in spite of the enormous amount of work which has been done in aerodynamics and the allied science of hydrodynamics, there is no satisfactory mathematical theory by which the forces on even the simplest bodies can be calculated with accuracy. Interestingly, the British had an alternative theory that they consciously decided to ignore. That was Lanchester's circulation theory of lift, or cyclic theory of lift. Lanchester was a practical engineer. He was very skillful in building engines and cars. He actually founded a company for this. And he was one of the two practical members in the committee. So obviously, he was outsider to the elite group from Cambridge. He had a serious interest in aerodynamics. In 1907, he published a treatise, 2 volumes. This is the first volume in aerodynamics, where he developed both 2D and 3D theories. Actually, he's the only one to work on the 2 versions of the theory. Like Kutta did 2D and didn't do 3D. Prandtl did 3D but not 2D. He's the only one to work in both. So his simple idea for the 2D was the 2D lift is actually due to a combination of a circulation and uniform flow. So somehow, as the wing moves through the air, it creates a circulatory flow, a circulation. But this circulation is not like a real vortex that we see in water where it moves with the flow. This is stationary to the wing, so he used the name bound to the wing. So this is why we call it now bound vortex. And if you accept this, theoretical description, then the lift can be determined from the famous relation rho-u-gamma. The fact that the combination of a circulation and uniform flow generates lift was not new. Actually, 30 years before, Rayleigh used the same idea to analyze this fancy problem of why a tennis ball swerves upon a cut. Interestingly, David Bloor was telling the story that Rayleigh was concerned with what they called real tennis or royal tennis. It's not our actual tennis. This was used to be played indoors, and players were allowed to use balls. So anyway, he was saying that it had very difficult set of rules, to the extent that it may take a couple of years from you to learn it, and you cannot write it in a document. You have to learn it in person. So David Bloor commented, clearly this was a game for wranglers. So Rayleigh was interested in analyzing this fancy problem, and he made an ideal model for it, which is the model of a rotating circle that, it's an ideal model for a rotating tennis ball. So as we all know now, Rayleigh hypothesized that the rotation of the cylinder induces a circulation, and once you have a circulation, he can get lift from this exact same formula, and probably this was the first time where one form of this formula be written. However, he actually wrote that friction is the immediate cause of the whirlpool motion, which is quite interesting. Remember, this is a very different lifting mechanism than just an airfoil moving through the air. But it's very different but similar at the same time, because we're saying here lift is due to circulation and here lift is due to circulation. They are using the exact same relation. So because of Rayleigh's status in the community at the time and the timing of this paper, this statement, formed the main understanding of lift in the British community of the time. In fact, here is an exercise. Go and open your Lamb book and look for this relation, where it is written. You will find it written in chapter 11, which is the chapter titled Viscosity. All right, so anyway, this is just on a side. We'll come back to it later. On Lanchester's 3D theory, he introduced the concept of a trailing vortex, a tip vortex. But not only that, this tip vortex is connected to the bound vortex on the wing that is responsible for the lift, in a way that satisfies Helmholtz's laws of vortex dynamics. If you read his statements, this man is not just a practitioner. He really had a deep understanding of fluid mechanics, and he knew what he was talking about. So this is his picture. Tip vortices induces a downward speed on the wing, which decreases the angle of attack, decreases the lift, and increases drag, as we all know. So the flow picture on the upper surface will be inward, on the lower surface will be outward. This is all his work. Complete ignorance by the ACA. So he wrote that Glazebrook, the chair of the committee always treated me as if I was appointed purely for my knowledge of the internal combustion engine. He didn't consider any knowledge in aerodynamics, you know. In fact, Bairstow used to laugh at him and mock him, you know, and just telling him bluntly, we don't believe in your theories, period. In fact, Lanchester, he sent 6 copies of his treatise on aerodynamics to 6 members of the committee. Only Rayleigh responded positively with copies of his papers. Another member acknowledged the receipt, and other 4 did not even respond, which is quite rude. So anyway, outside, not only inside the ACA, also outside the ACA, Lanchester was being rejected. Like, here is G.I. Taylor, the famous G.I. Taylor. In his Adams Prize essay, he actually rejected both theories. And he said, Mr. Lanchester loses the possibility of generating the motion from a state of rest by a movement of the solid. In searching for an explanation of the forces which act on solids moving through fluids, it is useless to confine one's attention to irrotational motion. He's basically saying if you start from rest, the flow is irrotational, it will remain irrotational. You will lose the capability of generating force. And this was the prevalent mindset in the community at the time, and I would say even until today. But there was an experiment in 1916 by Prandtl and Campbell at the committee. And they were doing something with horns and flaps and stuff. And they found actually evidence for Lanchester's work. They wrote, there is therefore some indication of the cyclical motion of the air round the wing, which has been assumed by Mr. Lanchester, which should have been a motivation for them to further pursue investigation of the theory, even though they completely ignored it, completely ignored the evidence. Here is a book 2 years later by Cowley and Levy, which was one of the most authoritative books in aerodynamics in the English literature at the time. They had a chapter called The Mathematical Theory of Fluid Motion, in which they discussed both theories, the discontinuity theory of lift of Rayleigh, the president, Lord Rayleigh, and also gave a couple of paragraphs to Lanchester theory. In these paragraphs they wrote, it can be shown that this force, the lift, is proportional to the intensity of the cyclic motion, gamma, and is thus apparently quite arbitrary. Fine, we agree with you. Ideal flow works. Lift is rho u gamma. How much is gamma? I mean, your ideal flow dynamics can say anything about gamma. So, in fact, they wrote a letter for him asking about the physical conditions that determine the cyclic constant. We know that this is a very hard question, so it remained open for so long. And he replied something like, okay, let's collaborate. So this was their conclusion from that chapter. The failure of the various treatments of the problem is evidently due to the supposition that the fluid is perfect. We need a viscous theory that will clarify at one stroke the whole problem of aerodynamics. And we are 100 years after that, and we still don't have this viscous theory. Anyway. The interesting question is that why the British aerodynamicists of the time ignored this evidence, which should have been a good motivation for them to further study the theory. Bloor provided a very interesting answer, relying on concepts from principles of scientific inference and Bayesian confirmation theory. Look at this. The probability of a hypothesis H, or a theory, given that, so after the discovery of an evidence E, is equal to the probability of the hypothesis prior to the discovery, divided by the probability of the evidence itself. So if a theory predicts some behavior, and that behavior was less probable, so the probability of it is small, and then we observe it, so the probability of the theory after the discovery should be larger, because you're dividing by a number that is less than 1. So the question was, why the probability of Lanchester's theory was not increased after the discovery of the evidence by Prandtl and Campbell? The only explanation from this equation is that this is 0, right? Which means that they have 0 degree of belief in Lanchester's. And this is summarized nicely by David Bloor. Psychologically, it means that if a scientist starts with a 0 degree of belief in a theory, then the subsequent course of belief will be wholly unresponsive to new evidence in its favor. It's a very important lesson in the history of science against prejudice and dogma. And unlike this response by the British, the German response to Lanchester was very different. In fact, in March 1908, Kutta scheme, he sent a letter to Lanchester requesting to translate his book into German. And September of the same year, Lanchester actually visited Germany, Gottingen in particular, and was hosted by Runge and his wife. So the question is, why did the British abandon Lanchester's theory and the German adopted it? That's the question. It actually boils down to a difference between physicists and engineers. This is from Lanchester's words himself. With the exception of Lord Rayleigh, the NPL did not take my work seriously. I believe because my methods did not appeal to them in view of their training. They mostly belonged to the Cambridge School, whereas I was a product of the Royal College of Science. So let me tell you some differences between their perspectives of the two schools. For example, on D'Alembert paradox, how they view it differently. So to the British, there's nothing paradoxical about it. Why? I mean, you invented a fictitious concept called ideal flow. So it's not surprising that it results in a zero force. You know, if this thing ever exists in life, it will behave this way, giving you zero resistance. Let's look at how the Germans viewed it. This is a 1911 experiment by Foreman. You know, I remember when we discussed how we construct the flows over shapes by playing with the functions f. Every function f differentiable will give me a shape. So he constructed 6 of these theoretical shapes. Here is one of them, all right? For which we know the theoretical solution everywhere. And he made these physical models out of these shapes and test them in the wind tunnel, compare the results. We know a priori that the theory will result in zero force, net force, for all these shapes. But he was interested in comparing the pressure distribution on the surface. And he actually found good matching between the two sets of data, the measured and the theory. Not only that, he found that for rounded nose, slender body, so small thickness, those shapes that are relevant to aeronautics, the resulting drag is quite small from experiment. And this drag is mostly due to friction, which means that if we're ignoring friction, the rest of the drag that is not due to friction is almost zero. So look at how Prandtl interpreted this result. The theoretical theorem that in the ideal fluid the resistance is zero receives in this a brilliant confirmation by experiment. And this is a stimulus to seek further relations between theoretical hydrodynamics and practical aeronautics. Look at the paper by Munk, one of Prandtl's best students. 1981 Annual Review Fluid Mechanics, looking 80 years back on his career in aerodynamics with Prandtl. The wind tunnel was asked whether the study of the motion of a perfect fluid was helpful for practical aerodynamics. And the wind tunnel answered with a loud yes. This was a very great achievement of Prandtl, one for which he did not get enough credit. So you can see the difference in mindset. The British viewed ideal fluids as fictitious. The zero force result is something natural for this fictitious concept. The Germans viewed the zero force result as a reasonable approximation for what is really happening in reality for shapes that are relevant to practical aeronautics. Let's look at another difference on their views on Navier-Stokes equations. These things are controversial. So Lamb wrote, you can open your Lamb book and find this. The hypothesis made above that the stresses are linear functions of the rate of strain is of a purely tentative character, meaning it has no basis. It's just a mere assumption. All right, and he followed. We have so far no assurance that it will hold generally. It was, however, pointed out by Reynolds that the equations have been put to a very severe test in the experiments of Poiseuille and others. So we can hardly hesitate to accept the equations as a complete statement of the laws of viscosity. Like, this is a very big statement. Actually, David Bloor commented, there is an immense authority behind this judgment. He's simply stamping the theory with the stamp of truth. This is the truth. It's a complete statement of the laws of viscosity. I don't know how he can write that, because at that time, these experiments on which he is relying on, they were for laminar flow. So fine, Navier-Stokes is valid for laminar flow. How can I be sure at that time that it will govern the turbulent flow at high Reynolds number? At that time, there is no guarantee at all. In fact, if you look, at that time we could not find an analytical solution for turbulent flow, and even nowadays, but it wasn't until relatively recently where we managed to solve, DNS, solve Navier-Stokes equation for a turbulent flow. Perhaps one of the first papers, if not the first, by Spallart. This is 1988, at a relatively high Reynolds number, and compared with the experiment, showed good matching. So how come, before this date and before these results, not necessarily that date, but before these results, how can I be 100% sure that Navier-Stokes equation will capture the turbulent flow field? This was certainly a very early claim of Vector-Lee by Lamb. And this was the Germans' attitude. So this is von Mises' hydraulic hypothesis. He's saying that the flow around an airfoil is doubtless a turbulent flow of a viscous fluid, of course. But if the small oscillations are disregarded, the remaining steady velocity values agree very well with those computed from the theory of perfect fluids. The viscosity is responsible for the continual fluctuations or for the turbulent character of the motion. This is his hypothesis. It's an assumption. All right? Look at this. Look at the next statement, which is now we can really laugh at it. It is left undecided whether the instantaneous fluctuating velocities of the real fluid follow the Navier-Stokes equations or not. She's basically saying that the average flow field at high Reynolds number will follow the ideal fluid dynamics. And we do not know whether the fluctuating field, the turbulent field, will follow Navier-Stokes equation. It's like we're sure of the ideal flow concept, we're not sure of the Navier-Stokes equation capturing the turbulent flow. And you have to put yourself in their shoes at the time. This is the knowledge that they knew at the time. Thanks to Abdurrahman for making this figure. So this is what they knew at the time. Let's say flow in a pipe. The blue is the laminar flow from Navier-Stokes. This is the only solution that they could get from Navier-Stokes equation at the time, right? Green is the naive solution from the ideal flow, unresponsive to the tangential walls. Red is the turbulent, which is closer to the turbulent. So you have to put yourself in their shoes at the time, all right? So anyway, he concluded by, it should be kept in mind that the viscous fluid, as well as the perfect fluid, are idealizations. And this is important, because sometimes we really take things for granted and we forget that Navier-Stokes is an idealization, right? So yes, of course, it should result in better results, but still, it's an idealization. It wasn't only the Germans, by the way, who viewed this. So here is an American mathematician, famous American mathematician, Truesdell, as late as 1955. He is writing, I could not accept the so-called derivation of the Navier-Stokes equations given in the textbooks. It seemed as unreasonable to suppose viscous stress, a linear function of rate of deformation, as to replace every curve by a straight line. So anyway, in summary, let me summarize the difference in views between the British and Germans. So British viewed ideal fluid as fictitious. In the words of Melville Jones, one of the later professors in aeronautics at Cambridge, he said, it was regarded purely as an exercise for the amusement of students. Material for examination boards like our prelim or something, but not for serious research. The Germans, on the other hand, they viewed ideal fluid as a good approximation, reasonable approximation of the average flow at high Reynolds number. That's a very different mindset between the two schools. British, they saw Navier-Stokes as the truth. To Germans, both are idealizations. One is better than the other, hopefully, but both are idealizations. For British, left is viscous, and if you really want left, go and solve Navier-Stokes equation. Don't waste your time doing anything else. For Germans, ideal fluid theory actually provides a reasonable estimate of the left for the cases relevant to aeronautics. I mean, I have the question here, really. We have two different schools, or two different set of scholars. They encountered the exact same physical facts, yet they arrived at very different conclusions. So the question is, why the Germans arrived at different conclusions than the British? And the answer simply lies in their training in technical schools. So for Europe at the time, for an educational institute to get the name of a university and status of a university, it must include some subjects like medicine, law, philosophy, theology. After the Industrial Revolution, there was a high need for engineering-focused schools, which resulted in this Technische Hochschule, or technical schools. Excuse my pronunciation for both German and English. But anyway, this was the result of this movement. They were deprived from the status of the name university. Okay? And in fact, they were not even allowed to grant doctoral degrees. It wasn't until recently, or late 1800, after a heroic effort from Felix Klein, the mathematician, they were allowed to grant doctoral degrees. In the very next year, Prandtl got a degree, PhD degree from TH Munich. Kutta did his postdoc at TH Munich. Felix Klein served as a chair, TH Munich. Prandtl was a chair at TH Hanover, and so on. So the educational philosophy at these THs at the time can be, expressively stated by Foppel. This was Prandtl advisor and father-in-law. At the time in Germany, it was very common to marry the daughter of your advisor. So Foppel wrote, "The natural scientist can wait for inspiration or more information." We can wait until we solve Navier-Stokes equation, fine. The engineer, by contrast, is subject to the force of necessity. When some phenomenon interferes itself in his path, he must arrive at a theoretical understanding of it as best he can. Let me give you an example of this, difference. On the arbitrariness of the circulation, gamma. Fine, we're gonna accept the ideal fluid concept. We're gonna accept lift that is rho u gamma. How on earth can we find gamma, right? So the ideal fluid dynamics does not provide any value for gamma. So it was really very good justification for the British school. The British school response was what? We need to solve Navier-Stokes equation to get gamma, right? That's the only way. Let's see the German response. The German response was, okay, let us look more deeply into that problem. Let us look on all the solutions corresponding to all the values of gamma. This is one solution for a small value of gamma, and consequently the lift is small because the lift is proportional to gamma. For this solution, the flow goes around the sharp trailing edge from the lower surface to the upper surface. Okay, let's look at another solution. Here's a solution for large value of gamma, consequently the lift is large. The flow goes around the edge from the upper surface to the lower surface. In both these scenarios, the flow goes around a sharp edge. It's as if you're turning in a zero radius of curvature, demanding infinitely high centripetal acceleration. So they do not look physical. Does this really happen in reality? Let's do an experiment and look at the flow field. Prandtl did the experiment in 1904 and visualized the flow field. Here is the flow field. Actually, neither scenario happened in reality. The two flows go smoothly together from the trailing edge. So fine, so let's specify gamma to do this for us. So we're gonna find gamma, the value of gamma is the one that makes the two flows come smoothly from the trailing edge. That's the Kutta condition that we teach nowadays in every single aeronautical engineering school, right? So this is engineering ingenuity at its best. To use physical observation to infer a mathematical condition that allows you to do things that you cannot do otherwise, right? Of course, this solution was not liked by the British school. Why? Because the Kutta condition is not derived from first principles, was not deduced from the governing equations, whether it's Navier-Stokes or Euler. And how did you get it? We get it from a physical observation, so it's an ad hoc condition, it's an empirical condition from a observation on a specific shape. What if I have a different shape that doesn't have a sharp edge? Or even your shape with a sharp edge, fine, but in, this sharp edge is not mathematically sharp. So why you're considering it as a mathematically sharp? That was the criticism from the British school. And really you can see now the difference. One way, on one school is trying to get a general theory that works for all shapes, account for all factors, viscosity and others. And the other school is just focusing on the problem of the time to come up with a good enough theory. This is well expressed by George Thomson. What is perhaps harder for the scientist to realize is the doctrine of good enough. The better is the enemy of the good. So the solution by the engineers was not less rigorous. It actually satisfies perfectly legitimate solution of the Euler equation. But it's not general, it serves the purpose. And that's the main difference. I have many other examples, frankly speaking, of the difference between the two. But let me, because I'm running out of time, let me go to the godfather. Prandtl. So, let me see how I'm doing on time, I don't know. Okay, yeah. So Prandtl, he actually got his PhD 1900 from TH Munich. Next year was at TH Hanover. 1904 made the historic paper of the boundary layer. So to see how effective is that. This is Goldstein in his Annual Review Fluid Mechanics paper, describing it as one of the most important contributions to science that was made during the 20th century. Look at Lighthill. Boundary layer to fluid mechanics is as special relativity to physics. Is so important. Why it's so important? Because it's perhaps the first time that allowed us to account for these both competing terms in a systematic way. When we do, we are used before that. We were used to account for one term but not the other. Like in ideal fluid, we can account for the inertial terms but not viscous terms. In the classical solutions that we teach in 230B in viscous flow, most, if not all of them, of course, we account for the viscous terms like laminar flow in a pipe, the Stokes oscillating problem, second problem. In all these problems, we account for the viscous term but not the inertial term. So this is perhaps the first time where we can account for the two in a systematic way, not just for a particular case, for most cases. And how he can do that? Because of his engineering ingenuity. Here is the brilliant assumption that has the two characteristics. One, it's reasonably accurate. Second, it's quite enabling. Because once you adopt this assumption into the equation, you arrive at a new set which are more tractable. You can even obtain analytical solutions. He used this formulation to estimate friction and boundary layer thickness, and even did boundary layer control, sucking the boundary layer inside the body, controlling separation. So as early as 1904, where people were even stumbling upon getting an ideal flow solution, what is the closure condition, is it Kutta condition or not, Prandtl was doing adult and serious analysis with viscous flow, getting friction, boundary layer thickness, and even doing boundary layer control. Of course, Felix Klein was among the audience. He was intrigued by Prandtl presentation, so he decided to attract him immediately to Gottingen. And in his nomination, he wrote that Prandtl combines the expert knowledge of the engineer with the mastery of the apparatus of mathematics and has a strong power of intuition combined with a great originality of thought. Indeed. Interestingly, Prandtl put the physical concept of the boundary layer, 1904 until today, more than 100 years, it's an open problem mathematics. It's still mathematicians are trying their very best to prove that Navier-Stokes solution converges to the solution of the Prandtl boundary layer equation inside and ideal flow outside. It's not proved mathematically yet. At Gottingen, he worked with engineers, Foreman, Betz, Munk, where he developed his other big theory, the Prandtl lifting line theory. So he adopted Lanchester's picture of the horseshoe vortex system, two trailing vortices connected to the bound vortex on the wing in a way that satisfies Helmholtz laws of vortex dynamics. His contribution was in the quantitative analysis, in the sense he made the analogy between an electric current in a wire and a vortex line, something like this vortex line. So similar to the fact that an electric current in a wire induces magnetic field in the surrounding, a vortex line induces velocity field to the surrounding. And both are governed by the Bairstow law. So he used the Bairstow law to obtain the induced velocity on the wing due to these two trailing vortices. So he can get how much lift is decreased and how much drag is increased. He also refined the picture by Lanchester. Instead of having one horseshoe vortex, he have infinitely many of these to have a continuous variation of circulation over the span and remove the singularity at the tip. And from this, he managed to obtain his famous two conversion formulas. By the way, Prandtl theory is not complete on its own. It cannot give you lift and drag, induced drag. It needs, in conjunction with the 2D theory, it can, but actually better than that. If you give me the lift and drag measurements of one wing, I can give you the lift and drag data for all other wings of the same profile but different aspect ratios. And in this regard, the theory is pretty damn accurate. So this saved tons of wind tunnel testing during the wartime. I'm done with, obviously this is engineering ingenuity, and we'll go to the physicists. You know, how about their physicists doing? Germany at the time, they had the goat, right? So how come they were not using him during the war, right? And indeed they did. Actually, he worked as a consultant on 2 airplane companies during the wartime. And if you want to learn about the efforts of the greatest physicist of all times for aerodynamics, you need to come to tomorrow's lecture. So thank you. Any questions?